Hello, my name is Jed Murdoch and welcome to Module 1 on Basic Population Growth. In this module we'll cover the characteristics of basic population growth and how you can model population growth. Population growth modeling has a lot of utility in terms of describing populations and how they change over time. So let's begin. Imagine yourself now in the plains of Colorado observing pronghorn. The pronghorn is really an iconic species of North America, of the West. It's one that's perhaps one of the fastest land mammals in the world, second only to probably the cheetah. And it happens to be a game species and one we're largely familiar with. Population managers, wildlife managers, those that may be monitoring pronghorn antelope are oftentimes concerned with characterizing that population and how it may in fact change from one year to the next. We may want to ensure that we have enough individuals over time so that that population is in fact viable. We may in fact want to ensure that we have a large enough population that it can withstand a certain amount of harvest, let's say, and still be consistent or viable or stable over the long term. So the population, a population, what is it? It's really one of those foundational units in biology. And a population is simply a group of organisms, a group of individuals of the same species that are occupying the same place at the same time, right? So with our pronghorn here that we've been dutifully watching, those pronghorn may be part of a population occurring in Colorado. So we oftentimes are concerned with charting population dynamics. In other words, the dynamics referring to how populations change in size over time, let's say in 1-year cycles or 5-year cycles, 10-year cycles, and so forth. And to do that, we really need to describe that population and model it. And that model gives us some power of prediction. So what do you suppose those factors are that really govern or control the way a population changes, its growth, let's say? What factors control that? Well, as you can imagine, births have a real important factor. The number of births in a population can certainly cause a population to increase. The births represent really an important factor that need to be considered in population dynamics. Similarly, those animals that die, as you can imagine, influence a population. We may have immigration being an important component as well. So we may have immigrants from a Wyoming population entering as immigrants into the Colorado population and joining that population. So certainly immigration in certain circumstances can be an important one. And then lastly, immigration. So the immigration of individuals from our Colorado population out to our Wyoming population causes perhaps a reduction in population. So these 4 factors, births, deaths, immigration, and emigration, in many ways govern population growth. They're key factors and they're often incorporated into population models. These factors are typically referred to as demographic processes, which is kind of a mouthful, but they are really just those factors. And typically we refer to them by a really nice acronym, the BIDE acronym, B-I-D-E, births, immigration, deaths, emigration. So these things together allow us to chart populations over time by describing a population. So in this module, we'll develop a basic population growth model. And in this case, we'll keep it relatively simple. We'll describe a population and really focus on 2 of those demographic processes. We'll focus on births and we'll focus on deaths. For the time being, we'll leave immigration and emigration aside just to keep it simple. But in reality, you can build these components into the model we'll cover in a relatively straightforward way. But for this module, just focus on a model related to births and deaths. And this model also will be a discrete time model. And what I mean by that is that the model will treat time not as though it's a continuous variable, something that is on a continuum, but rather that time occurs in discrete units. Those units might be years, They might be seasons, they might be days, they might be weeks, but we'll be charting population dynamics from one discrete time unit to the next. So from year 1 to year 2 to year 3 and so forth. So let's have a few look at the basic components of this model, and we'll continue to use the pronghorn as an example. So our model includes a few key components. The first one here is this value called NT. And NT is really just our population size at present, or perhaps at any arbitrary starting point. So it's where we start our estimation of population growth. This value NT plus 1, T plus 1 is what we estimate the population to be one time step into the future. So in the case of pronghorn, we may be estimating the population in 1 year's time, for example. So we may be using discrete 1-year time intervals. Another component here that we'll add is B sub t, and this is number of births. It's the raw number of births, and it's from the period t to t plus 1. So it's how many births occur during our time period. And then we also estimate the number of animals that died, or those that we lose during that period. And that's, of course, again, between t and t plus 1. We could tack on a couple of other components. I mentioned that we're not going to do that, but we, in some circumstances, add the number of immigrants here and the number of immigrants into our model. So our total overall model, if we did have those components then, would be our population size, which is a function of where we start, how many animals we start with, plus the number of animals that are born into the population. They add to our population. We then have those animals that die, so we have to subtract those from our estimates. Those are the ones that leave our population. And then if we wanted to, we could include the number of immigrants. So we're adding now the number of immigrants that join the population, and we would subtract the number of immigrants, those that leave, so these pronghorn perhaps, that leave our population and head up to Wyoming, for example. So we're going to take these values here and slice them off of our equation just to keep it a little bit simpler. So if we take those components off, we now have NT plus 1, so our pronghorn population, let's say, in 1 year's time being really our starting point population plus our number of births minus the number of deaths. Pretty straightforward, hey? So let's put a couple of numbers in there. If we're dealing with our pronghorn population that, let's say, is starting at 100 individuals, and in 1 year's time we have 25 individuals that are born and 10 individuals that die, we have what? We have 100 plus 25 minus 10, which, if I've done the math correctly, is 115 individuals. So this is really a pretty basic calculation, but it does form a framework for allowing us to make computations as to what we expect the population to be like, not only one time step into the future, but perhaps 2, 3, 4, 5, and so forth down the line.